And so buffers have some unique properties. One, is we have a mixture, a stable mixture of acid and base. Normally, if we have an acid and a base, they neutralize each other out. And so in this case, we'll have a weak acid and a weak base. What the biggest advantage of this is that it maintains a stable pH, or can maintain. It depends. As long as we have both components present, then it can maintain a fairly stable pH. And so what we can do is, if we take the buffer and add a little bit of strong acid, not too much strong acid. If you add too much strong acid, then what happens is you'll wipe out the base component of the buffer. So strong acid reacts with the weak base. And so the weak base will neutralize a little bit of strong acid that can be added. It depends on how much weak base. If you have a lot of weak base, then it can neutralize a lot of strong acid that you add. But if it's not so concentrated, then it won't. And so the pH will change, but it just changes slightly. Because what happens is, what you'll do is you'll form the conjugate acid of the weak base, and the conjugate acid is weak. And so we should be left with a weak base and weak acid in a slightly different ratio. That is a little bit less weak base and a little bit more weak acid. And so slight change in the pH. So we'll lose a little bit of this and gain a little bit of this, but the strong acid will have been neutralized. The same thing goes if we had a strong base here. If we add a strong base, then the weak acid in the buffer will neutralize that and form the conjugate base. The conjugate base is weak, and so we'll add additional weak base here. And so we'll lose a little bit of the acid and we'll gain a little bit of the base when that happens. And we maintain, there's going to be a slight change in pH here. But it's not a significant, when we add strong base to water, it's a much more significant change in the pH. And so let's look at some example calculations here. One example would be if we took just pure water. And let's take, let's say 250 milliliters of pure water, about a cup of water. And then we're going to add 1 drop of 6 molar HCl to this. 1 drop of 6 molar HCl. And then we're going to estimate the volume of the drop. This is not totally precise, but it's about 0.05 milliliters per drop. And it gives us about 20 drops to the milliliter. What would the new pH be here? So one thing is, whenever we mix the solution, all the 1 drop, is 1 drop going to change the volume of 250 much? No. But will 250 change the volume of 1 drop? Yeah, that's going to change the concentration significantly. And so what we're going to have here is a total volume of 250.05 milliliters. And we think, well, that barely changed from 250, but when we look at it from the perspective of 0.05, it was a huge change. And therefore, we're going to recalculate the concentration The first concentration we'll recalculate is concentration of HCl because this is a huge solution dilution. Solution dilution involves taking the volume initial divided by the volume final times the concentration initial. And so what that's going to result in is this. So the volume initial is 0.05. The volume final is 250.05 times the concentration initial, 6 molar. So what does this come out to here? .05 divided by 0.05 divided by 250.05 times 6. And the concentration of the HCl changed significantly. Now the concentration is 0.001199, 0.001996 molar. I'm not allowed this many sig figs, but we'll just carry some extra digits here. Now HCl is a strong acid, and we know the strong acids hydrolyze completely to form hydronium and chloride. K for this is very large. And so we take the strongest acid present, which would be HCl, and the strongest base present, which would be water. And then we can set up the ice table for this, but the ice table is complete. So this is going to be our initial, which is the 0.0019, etc. And we have water, this would be 0 and 0. So by the end of this, we're going to lose all the HCl, and we're going to be left with 0.00199976 molar hydronium. And the same for chloride. Now, this is going to give us pH, so I'll just take the log of this number, and we see that the pH goes to 2.9209. In other words, we're about 1 sig fig here, so the pH is going to be 2.9 here. Well, what did we start off with? Over here, if this is pure water at 25 degrees C, then the pH was 7.00. And so we went from a pH of 7 to a pH of 2.9, which means the water is considerably more acidic. Now, would you drink this? I probably wouldn't drink this. You know, at a pH of 2.9, it's getting pretty acidic.
Wouldn't that burn?
Yeah, it would irritate. It would burn, right? And so that's just with one drop of 6 molar HCl, which is dilute HCl to, let's say, a cup of water. Now, with the buffers have all kinds of pHs. You know, it depends on what the acid and the base is. You know, because there are a whole range of acids and a whole range of bases as far as strength goes. And therefore, there's a whole range of pHs that the buffers can adopt. And so next we're going to look, this is with pure water. Next we're going to look in a buffer. Pure water.
Would water be considered a buffer?
No, it's not a buffer because although, you know, water is the base here, it really didn't do anything to neutralize it in that sense. You'll see what happens with a buffer. So the next example is with a buffer. The first thing is, okay, there are many different buffer systems, and the buffer systems will have different pHs. So many different buffer systems. With many different pHs. And so we have buffers that are highly acidic, you know, and buffers that are highly basic. So it'll maintain an acidic pH or maintain a basic pH. And so you could do that. There's something called the optimum pH of a buffer. Okay, since there are many different, what we're going to do is we're going to look at HH buffers. What are HH buffers again? HH buffers are where the weak acid and the weak base are related. The weak acid and the weak base are conjugates of one another. Are conjugates. So typically we can represent that like this: HA and A minus. This would be the acid. This would be its conjugate base. Or B should just stand for B, BH plus. So this would be the base. That would be the acid conjugates of one another. So the optimum pH is based on the Henderson-Hasselbalch, and basically the optimum pH is where we have an acid to base ratio of 1 to 1. And so here we want a 1 to 1 ratio of acid and base. If we have a 1 to 1 ratio, then it doesn't matter. This is equally proficient at neutralizing acid as it is base. Now we could have a lopsided one. That is, a lopsided one would be where we have much more 1. Let's say we have lots of acid but very little base. That would be lopsided. And so that would be, if we had lots of acid but very little base, that would be good for adding strong base to it. But it wouldn't be so great if you add a lot of strong acid to it because of the capacity. And so when we have a 1 to 1 ratio of acid and base, we say that it has equal capacity for added acids and bases. Versus, it's not bad to have unequal capacities as long as you have adequate capacity overall. Let's say we have unequal capacity. Well, as long as the one that's the minor component, let's say I have lots of acid but little base, as long as that little base, is enough, as long as I have enough base that I don't exceed the capacity of the buffer. Exceeding the capacity of the buffer would be like adding so much strong base here that we completely neutralize all the weak base here, and all we're left with is the conjugate acid. And so if I add way too much acid here, if I add way too much acid here to neutralize all the base, then I'm going to have a solution of strong acid, weak acid. That's not a buffer. It would be strong acid, weak acid. pH would be dominated by how much extra strong acid there is. So, looking at the Henderson-Hasselbalch, the pH is equal to pKa plus the log of the base to acid ratio. Base to acid. Now, the base to acid, these have to be conjugates. And so the problem that a lot of people make, is, the mistake that a lot of people make is that they put any old base and any old acid here. No, you can't do that. And so sometimes, if it's sodium hydroxide here and HCl here, that doesn't work. They have to be conjugates and they have to be weak. They can't be strong and they can't be unrelated. Okay, so if we have a 1 to 1 ratio, then pH is equal to pKa plus the log of 1 to 1. Which means the optimum pH is equal to the pKa. So the optimum pH is just equal to the pKa, or the power of the Ka. So when we look at the Ka chart like this here, we can look at some examples here. examples would be something like acetic acid and acetate. If we look at the chart just does a dissociation like this. It's the same as 1.8 times 10 to the minus 5. So for acetic acid acetate, the optimum pH would be around 5, say, because the power of the Ka is around 4 to 5. Do you see that? If we calculate the pKa, then we'll figure it out precisely. When we do that, it comes out to 474. That would be it. So if I make a buffer like this, and I put in equal amounts of acetic acid. So let's say I put in 1 molar acetic acid and 1 molar like sodium acetate. That would give me my acetate that I need. So I'll have 1 molar acetic acid and 1 molar acetate. Then I know the pH for this is going to equal 4.74. And then I have equal amounts of both. But let's say, I don't want a buffer that's 474. I want a buffer that's pH 5. Well, the problem is when you look on the acid chart, is there an acid that has a Ka that is 1 times 10 to the minus 5? If there's, actually maybe there is. Looks like aluminum, right? But that's not going to be so easy to make, because we can't buy the penta-aqua, hydroxyaluminate ion, or aluminum 3 ion. And so oftentimes we don't have a pKa that's the desired pH. So for example, I want a pH of 4 or I want a pH of 5. What I could do is I could change the ratio. Sometimes or actually most of the times, the optimum pH is not the desired pH. Optimum pH is not the desired pH. And so the desired pH, let's say in this example, I want a pH of 5. Okay, pH of 5.00, that's desired. Well, what I can do is I can take, this one's kind of close. Do you see it's 474? So maybe what I need is a little bit higher pH. If I need a little bit higher pH, I need a little bit more base than acid. And so maybe that won't make it too lopsided. If I just add a little bit more base than acid. And so what I can do here is this. I can put in my desired pH, which is 5.00, and then calculate what I need for a ratio of base to acid. And so this is going to be the log. I'm going to use acetate and acetic acid for this. So I'll have that. So I know what my pKa is. My pKa is 474 plus this. And then I'll subtract that from both sides. So I'm going to get 0.26 is equal to the log of the base to acid ratio. And then I'll take the anti-log of that, both sides. So we get 10 to the 0.26 is equal to the base to acid ratio. And so what does that come out to? 10 to 0.26. That comes out to 1.8197. And so I need to mix it in this ratio. I need 1.8197 to 1 base to acid ratio. And so that means 1.8197 parts of acetate to every 1 part of acetic acid. Okay, and that's not too terribly lopsided. And so what we can do here then is we can make that. And so probably the easiest thing to do would be to, let's see, just to make a beaker like this, and we'll put in 1 molar acetic acid and 1.8197, as close as we can get, molar acetate. And then this buffer should have a pH of 5.00. We can confirm this by just checking, we just double check our calculation. And the pH is equal to pKa plus the log of 1.8197 divided by 1. What does that come out to? Well, I'm going to round it. I'm not going to carry all the digits in the calculator, so I'll just do 1.8197, take the log of that, plus 4.74. Then it comes out to 4.99999. And so it depends on how much we round this. Etc. So it's 5, pH 5. Now, this is a check. I don't have to use 1 and 1.8. They just have to be in this ratio. So I could use 0.1 and 0.18 because as long as it gives me the same ratio, I'm okay. Or I could use 0.01 and 0.101. Or I could use 0.001. But the thing is, the more dilute you make this, the less capacity it has. The more concentrated you make it, the higher the capacity it has. And so we want to make it with, but then again, it's a cost issue. The more concentrated you make it, the more expensive it's going to be, and you need that capacity. And so you have to look at the intended use for the buffer. Do you need high capacity? So for example, if I needed really high capacity, could I make this 181? Well, the problem is can you make a 181 molar solution of acetic acid? No, you can't. It's impossible. You can't fit that many moles of acetic acid into a liter.
Anything 181 molar? That's way too much.
No, it's way too much. I mean, think about pure water. Pure water is 55.5 molar. Maybe you can. I don't know what gold would be, or something very small, beryllium, solid beryllium. Gold packs most efficiently. Hexagonal and cubic closest packing are the most efficient packing. I haven't calculated the molarities for gold, but it would be interesting to see what it is, but I doubt it's going to be anything close to that. Gases are, mostly empty space. And if you want, you have to pack. The reason why I say it's not possible to get 181 molar is because the volumes take up volume. And so the situation is this. If you have a liter, you can't fit that many atoms in the liter. If you have 181 moles, you're going to exceed that volume. It depends on how it packs. And so, anyway, going back to this. So as long as we have this ratio, we're okay. That's fine. So now I have my pH 5 buffer. Can I use the same one? I'm going to make, I don't want 5. I want pH 7. So let's let's use this and try to make it pH 7 because I want to make it match with water. And so the next example is I'm going to try to make a pH 7.00 buffer is desired. Because what I want to do is I want to compare this to pure water. Pure water is pH 7 unbuffered. How does that compare to a buffered solution? And so if I do a pH 7.00 buffer, which is desired, let's see. Get this. Then that's easy. I'll just do pH is equal to the pKa plus the log of the base to acid. In this case, the pKa is going to be for acetic acid. That's the acid. And the base is acetate. And the acid is acetic acid. And they're both weak and they're conjugates of one another. And so I'll do the same thing. I'm going to solve this for the base to acid ratio. Which is going to equal, okay, so this is 7.00. This is 4.74. So if I subtract 474 from both sides, I'm going to get 2.26. And then I'm going to take the antilog. So this is going to be the antilog of 2.26. Let's see what we get here. $181. One. So one thing I might try to do is I might try to make this $181.97 molar acetate and 1 molar acetic acid. I might try to do that. But do you know what pure acetic acid's molarity is? If you have a liter of pure acetic acid, how much volume does it take out? I mean, it takes up a liter, but how many moles can you fit into that liter? Well, as pure acetic acid as you can get is a liquid, for one, and it's called glacial acetic acid. And glacial acetic acid will take on some water from the air, you know. And so we can take a look at glacial acetic acid briefly and see if it's feasible or not feasible to get such high concentrations as the acetate. Or we could look at pure sodium acetate, you know, without any water. Let's do that. Okay, this was having difficulty earlier. Okay. So we could do a quick calculation here. This is pure sodium acetate, which is a solid. And so this is as concentrated. This is a weird formula, isn't that? Mm-hmm. A weird formula. It's wrong. I don't know why nobody's corrected it. But anyway, that goes to show you Wikipedia can sometimes be pretty reliable, and sometimes it's not very reliable. And that's totally wrong. Okay, so we have this 82, okay, we have a density of 1.53 grams per cubic centimeter. And so we'll have 1,000 cubic centimeters in a liter. And so we'll do that. It's going to be 1,000 times 1.53, which gives us 1,530 grams in a liter. And there's 82 grams per mole. So divided by 82.0343. And so in a liter of pure solid sodium acetate, we can only fit 18 moles. That's it. Then we got to dissolve it in water. And so it's going to be a lot less than 18 molar. Well, there's absolutely no way that, because the atoms stay the same. Pure acetic acid is called a glacial acetic acid. And let's see. We can also do the calculation for glacial acetic acid based on its density. Here. Pure acetic acid. This one is an acidic. Vinegar is, okay. Has a density of 1.05, so close to water density. So I'm going to have 1,050 grams of acetic acid in a liter. And then there's 60 grams per mole, so divided by 60.05. Excuse me, so pure acetic acid, I can only fit 17 moles of pure acetic acid in a liter. Okay, that's even less than water. Water, I can fit 55.5 moles in a liter because a mole only weighs 18 grams. So these are impossible. That's pretty much impossible. So even 18 is getting impossible. So I could go maybe 1.8197 molar acetate to, okay, so I'll move this 2 decimal places over to 0.001 molar acetic acid. Now take a look at what happens to the capacity. We have plenty of capacity in acetate, but do we have much of capacity in acetic acid? No. And so here, we have 1,000 times less, 1,000 times less acid approximately than base. And so this is what we call lopsided. This is not going to be a very effective buffer. And so we have something that's called the buffer range. The buffer range is this. When we have, let's say, 1,000 to 1 ratio, approximately, that's not so great because the capacity to neutralize added acid in this case would be excellent. The capacity to neutralize added base would be quickly overwhelmed. We'd quickly exceed this capacity here. And therefore, we have the optimum buffer range. So we have an optimum pH. And then we're going to have something called the buffer range. Buffer range is just saying we don't want to make too lopsided of it. And so the buffer range, when we're looking at the base to acid ratio, we like to keep it within this range. We like to keep it within a 1 to 10 range. So maybe we have 10 parts more acid than base. That's okay. It's close. Okay, to a 10 to 1 range. But if we go to 100 to 1 or 1 to 100, that's exceeding the range. And so the best is, of course, a 1 to 1 range. If we have a 1 to 1 range, it's quite nice. And so what it works out to is this. A 1 to 1 range the pH is equal to the pKa. A 1 to 10 range here, the pH is equal to the pKa minus 1. How do we get that? Well, we get that from this equation. The pH is equal to pKa plus the log. And if we put in the ratio here, the 1 to 10 ratio, the log of 1/10 is minus 1. It's 10 to the minus 1. And so therefore we get a pKa of minus 1. And then over here, if we plug in this comes out to pKa plus 1. That is, the pH is equal to the pKa plus the log, and the ratio we put in here would be a 10-to-1 ratio, or 10 to the first, which is just going to give us 1. And so what we can do for acetic acid is we can map out its optimum pH, the acetic acid acetate buffer system. So for the acetic acid, I'm going to call it HAC, that's acetic acid abbreviation. And acetate, I'll just say AC minus, this will be acetate. Ion. Then we have this. The optimum pH is going to be 474. And then the buffer range, what we can make it a suitable buffer for, should be between 374 and 574. So for this buffer system, you could feel comfortable making a buffer anywhere from 3 3/4 to about 5 3/4. It's still a gray area. I mean, if you're at 3, 5, 7, 8, it doesn't really make that big a difference now. But this will keep it between a 1 to 10 ratio to 10 to 1 ratio base to acid. And so if I wanted a buffer of 4.00, then this is fine. I could use this buffer. If I wanted a buffer at 5.0, we just did it. If we wanted a buffer at 4.5, we could do it. But if I want a buffer at 3.5, I probably should search for a better buffer system. And if I want a buffer at pH 7, well, pH 7, this is outside the range. This is outside the range. And so what does outside the range mean? Outside the range means it's going to be way too lopsided. You're going to have way too much of one and not enough of the other. That's what outside the range means here. So what we want is we want a pH 7 buffer. So we have to first figure out what system we're going to use for a pH 7 buffer. And so let's take a look at the Ka chart or pKa chart. If we have a pKa chart, it's a little easier because if we have a Ka chart, then we have to look at the power and kind of estimate what it is. So let's take a look at some acids here. Okay, I can't use that. This is a good figure here. I guess we can use the one in our book too. But this is kind of an interesting chart because this chart they calculate the KBs. That's unusual. That's good. So what we're looking for is we're looking for a power of around 7. And when we look, okay, this is close. This is 7.9. This is almost 10. 10 to, actually 10 to the minus 6 would be 1 times 10 to the minus 5. This is getting farther. This is not. Well, plus, this is too hard to work with. As is this. This is okay. 4.2 times 10 to the minus 7 is probably close. But carbonic acid is too hard to work with. Carbonic acid is unstable. You can't weigh it easily. This one, the hexaoxyl complex of copper 2, yeah, but this is difficult because this hydroxyl complex, we can't buy this stuff. We have to make it. So that's not so good. Oh, this is perfect. Look at this. This has a pKa of exactly 7 relative to 1 sig fig. It's perfect, but there's a problem with H2S. There are two problems with H2S or more. One of the problems with H2S is, do you know? It stinks. You know what it smells like? Rotten. Another problem with H2S is it's toxic. It's toxic at the part per billion level. And so, do you want to work with a toxic substance? No. The other problem is the solubility. The solubility of H2S is only 0.1 molar. That is, the maximum amount of H2S you can get in solution is 0.1 molar. So it's not going to make a very high capacity buffer, 0.1 molar. So even though this seemed perfect, it's not. However, how about dihydrogen phosphate? Dihydrogen phosphate is close. 10 times 10 to the minus 8 is 1 times 10 to the minus 7. So this is very close. And so let's go with dihydrogen phosphate. Okay, and so the first thing is, what is the pKa for dihydrogen phosphate? So we want a pH 7 buffer. I'm going to get it to 2 sig figs buffer. And so first we got to pick the acid. We want an acid with a pKa close to 7. So choose an acid with a pKa close to 7. And we came up with the acid here. We could also use hydrogen sulfide ion, which is close. We could use hypochlorous acid. I don't want to use lead. And so these would be acceptable too, as well. But we'll just go with dihydrogen phosphate. Since, actually, hydrogen sulfide would be equally as close. So we have dihydrogen phosphate with a Ka of 6.2 times 10 to the minus 8. I think our book is 6.3 times 10 to the minus 8. And you'll see a little bit of variation depending on the year of the chart and the source. But I think Petrucci is pretty up to date. What does our chart here say for dihydrogen phosphate? 6.23. Okay, 6.2 is probably good. We can take a look. Yeah. Our book has a Ka of 6.3 times 10 to the minus 8, so I'm going to just use the one from our book. Since that chart, I don't know the source of the chart, and that chart's old there. So, all right, so what is the pKa first off? So let's go ahead and calculate the pKa, which would be 10 to the minus 6.3 times 10 to the minus 8. Or actually, oops, sorry, wrong. It's the negative log. pKa is the negative log of 6.3 times 10 to the minus 8. 6.3 times 10 to the minus 8. 7.20. 7.200. I'm only going to go 2 sig figs, so let's just call it 7.20. Calculation a little easier. I can carry more digits if I want to be more precise, and then round the Okay, so what I need to do is I need a little bit more what?
Base.
Need a little bit more base to, actually no, the base would bring up the pH. I need a little bit more acid to bring down the pH. If I have a 1-to-1 ratio, it's going to come out to 7.20. Now, if this is my acid, what is my base?
HPO4 2 minus.
Yeah, the base is going to be HPO4 2 minus. This would be the conjugate base of that. And so these would be conjugate pairs of one another. And so I need just a little bit more acid. So the pKa plus the log of base, HPO4 2 minus, to acid, H2PO4 minus. And so the pH that I want is 7.00. The pKa that I have is 7.20, just slightly off, plus the log. And I'm just going to call this B over A. So I don't have to write that over, And so the base to acid ratio, just subtract that from both sides, so is going to equal 10 to the minus 0.20. I have my calculator here. So I get a 0.63096 over 1 ratio. And so if I made the base 1, I'd need 0.63096 molar acid. Or I could flip this over. If I flip this over, I can make the acid 1. So if I invert this, or it would be 1 part of acid to every 1.5849 parts of base, more base, or any ratio, any equivalent ratio. So I'm going to up the capacity, 0.63 is like a half molar. I'm going to go with 1 and 1.5. 1.58 molar should be easy to make. Let's do that. So I'll probably use the sodium salt of these. If I use the sodium salts of these, so I'm going to make this, let's see, I'm going to use this one. So I'm going to make this 1 molar base. And the sodium salt of that would be Na2HPO4, sodium monohydrogen phosphate. And then I'm going to make it 1.5849 molar sodium dihydrogen phosphate. And then the pH should work out. Let's see what the pH works out to. Okay, if I round this to 1.58, what would my pH work out to? Actually, how many things am I going for? Is equal to pKa plus the log of 1 to 1.58. Let me just round that and see. So I'm going to go 1 divided by 1.58 equals, take the log of that, and then add it to 7.20 plus 7.2. Okay, it works out okay. The pH comes out to 7.001. So even if I round this to 1.58, I'm still going to get 7.00.
If we take the inverse of base over acid, wouldn't the new thing be acid over base 1 over 1.58?
No, I'm just inverting the numbers. I'm leaving it's just so I didn't get a different ratio easily. it's still base acid. I didn't invert this. I just inverted the numbers. So the only reason I inverted it is here, if I leave it as this is per part of acid. If I invert it, I can get per part of base. So for every 1 part of base, I need this many parts of acid. For every 1 part of acid, I need this many parts of base. And so it's just 2 ways. You can do this rapidly by just inverting the numbers in your calculator, but you always have to leave it base to acid. Here, if this were acid, then the pH would be going down by 0.2, not up by 0.2. Okay. Next, what we're going to do is we're going to add 1 drop of HCl to this. All right, so I have my pH 7 buffer. Do you have this? Let me just do that. So the next example is I'm going to add some acid to the buffer. So we're going to test the buffer. So we're going to add 1 drop of 6 molar HCl to this buffer. See what happens to pH. So to make it fair, I'm going to use 250 milliliters of buffer. And the buffer is going to be 1.58 molar base, which is going to be the monohydrogen phosphate, to I'll call it 1.00 molar acid, which is the dihydrogen phosphate. So again, I have a little bit more. No, this is wrong, right? I need a little bit more acid. And so I have these flipped. It's 1.58 molar acid, H2PO4 minus, to every 1 molar base, HPO4 2 minus. The only reason is to just increase the capacity a little bit. You know, the more concentrated, the higher the capacity. The more concentrated it is, the less susceptible to changes in pH we want to observe. And then I'm going to add 0.05 milliliters of 6 molar HCl. This is 1 drop. And let's see what happens to pH. Originally, this is pH 7.00. The first thing I have to do is solution dilution. I call this step I. In chapter 17, we're going to be doing step I a lot. Step I is solution dilution. And since we're dealing with a lot of mixtures in chapter 17, this is the initial step we have to do before we do any kind of reaction. And so we're going to figure out the new concentrations of everything. And so this is going to be 250.05 milliliters here. And we'll figure out the new concentration of HCl. Well, the new concentration is going to be just the same as we had before, which is our initial 0.05 over a final 250.05 times the initial concentration, 6 molar. And that came out to what? It's going to come out to this, what we had before, which is 0.05 divided by 250.05 times 6. 0.001998 molar HCl. Okay. Now, these didn't change much, but we'll go ahead and calculate it. for the H2PO4 minus. The H2PO4 minus had an initial of 250 and a final of 250.05. So initial over final times the initial concentration, 1.58 molar. And so that's 250 to 250.05 dilution. This is called the dilution factor, times 1.58. This gives us 1.5797 molar. And then I'm going to do the HPO4 2 minus, which is going to have the same dilution factor. It's a 250 to 250.05 dilution of 1.00 molar. So 250 divided by 250.05. That's going to give us 99980. I'll just go 9998. Okay, I'm not allowed this many sig figs, but I'm going to carry it to avoid rounding error. Okay, once we do the solution dilution, then we go to step 1. Whenever we deal with mixtures in chapter 17, what we do is we take the strongest acid and react it with the strongest base. So take the strongest acid present plus strongest base. What is the strongest acid present here?
HCl.
HCl. So this is my step 1, HCl. What is the strongest base present? Water. In chapter 16, it was always water. But in this chapter, we have a stronger base than water. You know, definitely water is there, but there's a stronger base than water. HPO4 2 minus is a stronger base than water. Okay, so what forms here? This is an acid, a proton donor. So we're going to form chloride, and this is a base, a proton acceptor. We're going to form H2PO4 minus. Now we need K for this. This is not Ka, right? And this is not Kb. This is K reaction. And so we need the K for this reaction. Do you see it on the chart? No. It's not on the chart. And so there is a little side note here. Strong electrolytes, strong acids, strong bases, react to completion. Strong react to completion. So the example of this would be here. If I had HCl plus water, is water a very good base? It's not that great of a base. HCl plus water, we know the Ka for this. Ka is very large. And water is an exceptionally weak base. If you go to the base chart, where is water ranked on the base chart? The strongest base on this chart is amide. And then when you look at water, it's way up there. You see it? It's next to like bisulfate nitrate chloride. You know, chloride is a very good base? No, I mean water is better than that. All right, so we have water. If we have HCl plus a weak base, no, all the weak bases are stronger than water. Do you see that on the chart? All the weak bases, all the bases above water are neutral. And so all the weak bases are stronger than water. If it's stronger than water, then we're taking the acid and react it with a stronger base, which makes the reaction more favorable. And so K we estimate to be very, very large, because rather than reacting with water, we're reacting with a weak base. What if we take HCl and react it with a strong base? then that's even more favorable and has an even bigger driving force for this. And so if we take HCl and react with that as a strong acid plus a strong base, this is not A, this is K reaction, sorry. This is K reaction. K reaction is going to be very, very, very large. The stronger the acid and the stronger the base, the more favorable that reaction is. And so here we have the scenario of strong acid, weak base. Therefore, K is going to be very, very large. Now, what we have to do is we have to move the values from step I to step 1. So the HCl will move over here. And then the H2PO4 minus, we're going to move over here. And then the HPO4 2 minus, we're going to put here. And so we're just going to carry it down from step I to step 1. And so the initial here is going to be 0.001998 molar. The initial here is going to be 0.9998 molar. Chloride is going to be the same as this. Or actually, no, chloride's not going to be here. It's 0 because the chloride's wrapped up in the HCl. It's not separate. And the dihydrogen phosphate is going to be 1.5797 molar here. And so those are our initials. And so the change is going to be complete. So which is the limiting reagent here? HCl. So we're going to lose all of it. 1998. And so at the end of this, we should have 0 molar. That's our limiting reagent is completely consumed. We're going to have some excess reagent left over. So it's going to be, what is it going to be? I'm just going to calculate it. That minus 0.001998, 0.9978. So I'm going to get 0.9978 molar here. And then the chloride I'm going to have is 0.001998 molar. And here I'm going to get plus 0.001998 molar. And so 1.5797 plus 0.001998. And I'm going to get 1.5817 molar. And so essentially what happened was the buffer neutralized the added acid. And the result of that is the ratio changed. Did the ratio change a lot or not? So when we look at the ratio, the original buffer ratio was 9998 to 15797. After the addition of the HCl, the ratio went from 9998 to 9978 and then 15817. So the ratio did change. But what's going to happen to the pH based on this ratio change? And so this is what we do is step 1, we leave. Step 2, we determine what's left over. Determine what remains. In this case, what remains is chloride's neutral. What remains is the buffer. And so the buffer remains. Okay, so we go on to step 3. Step 3 is we'll just calculate the pH of the buffer. And so the pH is going to equal 7.20 plus the log of the base. This is the base. It's going to be 9978 now. Over the acid, which is going to be 1.5817. And so I'll go 0.9978. .9978 divided by 1.5817. Take the log of that answer plus 7.2. And I got an pH of 6.9999. Did the pH change much? No, the pH barely changed at all. In fact, the 2 degrees, the pH didn't change. pH is still 7.00. Now, higher capacity buffers will see an even smaller change. Because this is the change here. And so if I had a higher capacity, let's say rather than I had 0.9, let's say I had 9.9. If I had 9.9, this would be barely any impact on that. That would be a negligible change. And if this were 15, if I could get this to 15, I probably couldn't get to 15, but if I could get this to 15, then this is a negligible change. However, lower capacity buffers, we're going to see a more significant change. So if let's say my initial were 0.009. If my initial were 0.009, that's going to be a huge percentage change. Do you see that? What if my initial were 0.0009? If my initial were 0.0009, then I switched it. What's the limiting reagent now? If this were 0.0009 and this were 001, then this would be my limiting reagent, and I'd completely consume this and I'd have excess HCl left over. That's called exceeding the capacity of the buffer. I overwhelmed the buffer because I've consumed all of one component. You don't want to do that. You want to make sure you have plenty of buffer component to absorb these changes. And so that would be too low of a capacity, although it would still have the same initial pH, pH 7, because the ratio is the same. If I went with a low capacity buffer like that, over here. So I'm going to go 1,000 times less concentrated. I'll dilute this, which would be like 1,000 to 1 dilution. So 1 part of this, 999 parts of water. I'm just going to dilute it. And so an example of this would be if I had these concentrations. pH would be the same. This should still be a pH 7.00 because the ratio didn't change. But this is low capacity. And this buffer would not be able to handle 1 drop of HCl. Right? It would, the pH would change significantly. pH changes significantly. With 1 drop of HCl. Do you want to see the calculation or skip the calculation? You want to see it? Okay. So let's say I already added my 1 drop. So this is going to be 0.001998 molar HCl. Because I have 250 milliliters of this low capacity buffer. And so this is after step I. So step I is the solution dilution. We finished the solution dilution. Now we go on to step 1. Step 1 is the strongest acid plus the strongest base, which is what we have up here. So the strongest acid present will be HCl. The strongest base present will be the monohydrogen phosphate. You can just look that up on the chart. And this is going to form chloride plus dihydrogen phosphate. And then we'll carry the concentrations from step I to step 1. So the HCl goes here. It's going to be 0.001998 mole. And then the monohydrogen phosphate would be 0.000 9998 mole. Chloride's going to be 0. And the dihydrogen phosphate will be 0.00015797 molar. Okay, that's our initial. Then we look, the change is going to be complete. So we look at the limiting reagent, and now the limiting reagent is this. And so we're going to lose all of this. 998 molar, and that gives us 0 molar monohydrogen phosphate left over. This one, we're going to lose minus 0.000998. So what does that give us? I'll just calculate it in the calculator. 0.001998 minus 0.0009998. And it gives us 0.0009982. And over here, I'm going to chloride doesn't make any impact on the pH. And so we'll just add it over here, 9998. So 0.0015797 plus 0.0009998. Okay, I get 0.00255795. Okay, then the next step is, okay, this is step 1. Step 2, we analyze what's left over. What remains. When we analyze what remains, we have this. We have strong acid, HCl, and we have this. This was the acid. Remember, this was the acid of a buffer, but this is amphoteric. So was the acid, but H2PO4 minus is amphoteric, which means it can also act as a base. And it turns out that H2PO4 minus for water is stronger base. So we go over to the base part and take a look. Which one is stronger base? Let's see if this has. H2PO4 minus is stronger than water. So we repeat, react strongest acid remaining its strongest base remaining. Well, I was going to show the acid base chart here, but basically you can see it. Where H2PO is stronger than water. And so we have to look at the roles. You know, the roles can change when we go from step to step. And so we take the strongest acid, HCl, and react it with the strongest base present, H2PO4 minus. What do we form? The acid loses a proton, form chloride, and the base gains a proton. In this case, it's going to form phosphoric acid. This one turns out to be a more complicated problem. Sometimes, you know, we're just looking chloride and excess HCl, so then it's pretty easy, but this one is a little more complex. And so what we're going to do is we're going to carry down the concentrations here. So we carry the HCl down, and we're going to get 0.0009982. And then we'll carry down the H2PO4 minus. Okay. We carry this down, it's going to be 00, 25, 79, 5. We'll carry down the chloride. The chloride's not going to have much impact. So I'll go ahead and bring it down here. It's 000, 99, 98. And then H3PO4 is going to be 0. What's K for this reaction? Yeah. The K of this reaction is going to be very, very large. So it's going to go to completion. So we got to look, what is the limiting reagent here? The limiting reagent is HCl. And so the change here is going to be complete 0.0009982 molar. And so equilibrium will have 0 molar. And then over here, I'm going to have minus 0.0009982. So I'm going to just bunch that in my calculator. I don't want to do too much. So this is 00.0025795 minus 0.0009982. I get 0.0015813. 0.0015813. Okay, then the chloride, I'm going to add this 0009982. So I have 0009998 plus 0009982. This gives me 001998. And then this is going to be plus this, which is going to give me 0009982. Okay, then what I need to do is I need to analyze what remains. You know, this will be, okay, this was step 2. This is step 3 here. And so analyze what remains after this step. And so what do I have? It's a mixture. But what type of mixture is it? Is it a strong acid, weak acid mixture, or what? No, there's no more strong acid left. What kind of mixture is that? Yeah, one thing you notice is they're conjugates one another. And in fact, which one would be the acid? This will be the acid and its conjugate base. Are they both weak? They're both weak. So if you have a weak acid, weak base, and they're both conjugates of one another, we call that a HH buffer. This is an HH buffer, but it's not the same buffer that we started with. We just made a new buffer. Well, let's see what the pH of this buffer is going to be. So what we see is analyze what remains. We have an HH buffer that remains. So an HH buffer. Right here. Well, if we have an HH buffer, then we're going to use the HH equation for the HH buffer. And I'm not going to do an ice, of course we could do an ice table. Ice table is we just pick the Ka or the Kb. It's not necessary to do that. And so the next step, which is, this would be what's step 2, that's step 3, or no, step 1, yeah, this is step 1, sorry. It'll be step 2. And then we're on step 3. Are we out? Yeah. All right, we'll finish this next time. Okay, I'll stop here. Better take a picture of this so I can get the concentrations next time.